All right, so I think the fundamental question that sort of kicks off the Zeroth Law, which I think was the fourth one they actually thought of, but considered more fundamental. What does, if I have a typical glass thermometer sitting in the room, what does it measure? No.
Its own.
Much closer. What do you mean by its own?
Like whatever it's made of.
The temperature of the glass.
Yeah.
Not the glass. The other part.
The stuff inside it.
Yeah, the stuff inside it. I always think mercury, but I know mercury thermometers
Yeah, that's what I was gonna say.
are rarer. It's whatever's inside it. So we have this, some sort of liquid encased in glass. I'm assuming your drawing will be much better than that. And as energy gets put into the liquid, it will expand. We've talked about that already. And so it will expand, and so there are some materials that work quite nicely for how much it will expand, considering how much energy is put into it. And that is, I haven't done the lab in a while just because it's a real nuisance, but it is one of my favorite labs where you can do this where instead of having a liquid inside the thermometer, you could have a gas inside the thermometer. So if I just take a normal soda straw and I seal off the end, and I get an air bubble in here, so I have air right here, and then water right here. Air is going to expand much more than water will under a certain temperature, so you take this and you can put it in various objects and just mark off on the straw how big the air column is depending upon a certain temperature. Now, done well, you will be able to, it'll be some linear progression, and then you can start measuring temperatures with it. The downside is it's so easy to mess up. If you do it really well, I've seen it done in 15 minutes, and I've seen it, students still struggling after 2 hours. It's that kind of lab. Either you hit it right, or you are just experiencing one frustration after another. Matter of fact, with that, since you can do a couple different temperatures here, body temperature, air temperature, ice, boiling water, you get easily four different temperature spots. Then, working backwards, you can actually predict what absolute zero is doing this. Figuring at absolute zero, that the volume of this would be so close to zero that we'll just pretend it is zero. However, back to the Zeroth Law. So what a thermometer measures is really just the temperature of the liquid here. Now you assume that the liquid is the same temperature as the glass. You assume that the glass is the same temperature as the air surrounding the glass. You assume the air surrounding the glass is the same temperature as the air just past that, and so on. And so that way, indirectly, we measure the room temperature. But we make certain assumptions. Well, the Zeroth Law is what I consider to be the transitive property of thermodynamics. So flash back to math class. What is the transitive property? It's one of those things in math that I always considered so incredibly obvious. Start you out. If A equals B, that's a reflexive property, sorry, and B equals C, there we go, then,
A equals C.
yep, that's the transitive property in math. transitive property of equality. That's an equal sign there. So over here, we got to, basically, we're taking that, except we got to throw a lot more words into it because it's thermodynamics. If system A is in thermal equilibrium with system B, and system B is in thermal equilibrium with system C, then system A is in thermal equilibrium with system C. In other words, if the liquid is in thermal equilibrium with the glass, and the glass is in thermal equilibrium with the air, then the liquid must be in equilibrium with the air. Now, what's thermal equilibrium? Inquiring minds want to know. I assume I threw all those down there. Heat flows from hot to cold, usually. Thermal equilibrium means change in temperature is statistically zero. And I can do another definition which has 10 times more words, but that's the essence of it. Now the reason why I didn't say zero is that it is possible. I got molecules in these two. I have molecules in the water. I have molecules in the glass. They're bouncing up against each other, and there will locally I could have. It is possible for the glass to get a little bit hotter and the liquid to get a little bit cooler, but I'm just as likely for that to happen as the opposite to happen. So on the whole, there's not really a change in temperature, but locally I could have it happen. It is possible for temperature changes to flow the opposite of what we would expect. It is a non-zero probability, although it is small. It is possible for a lake to freeze in the middle of summer. It's just the odds are against it. All right, questions about the Zeroth Law of Thermodynamics? First law we talked about on the very first day. And this is just conservation of energy. So I have heat flowing in, I have heat flowing out, I have work being done. In essence, I start out with a certain amount of energy.
What did I say? Conservation of
Energy. I even tried to write it more neatly than I had. Slightly better. My initial energy plus any amount of heat in minus any amount of energy out, which is generally symbolized by work, is equal to energy final. And I can change letters around, I can put things on other sides of the equation, but in essence, I start out with a certain amount of energy, I put something in, something comes out, I end up with a final amount. We talked about how some textbooks will have all the signs will have these signs opposite because of what you consider to be the system. And now we're about to get to the second law of thermodynamics, the one that I consider to be the depressing one. All right, so this one comes in many forms. So we could word it as we can never break even. In other words, I have a system here, and I put, let's say it starts out with my initial amount of energy is 10 joules. I put 20 joules of energy into it. So therefore, how much energy does it have now? And now I want this system to do work. So you can treat this as, there's some kid, you feed them, they have all this energy now, and you want them to do work. Ideally, they can do 30 joules, or this object can do 30 joules of work, because it's got this 30 joules of energy. If it completely expends it all, it will do 30 joules of work. What the second law tells us is no. That it will do work, and it will just lose some. It is impossible to break even. If 30 joules of energy in does not translate to being able to do 30 joules of work out. You will never break even. The perpetual motion machine says that I have a machine here which takes 25 joules to run. If perpetual motion machines were possible, this machine would produce 25 joules of energy, which you can just feed right back into itself. And so it takes 25 joules in, it uses 25 joules to make itself run, and so you have perpetual motion. This cannot happen, according to the second law of thermodynamics. Now, occasionally, I have seen in the news of someone coming up with a new perpetual motion machine, or something where you get more out than you put in, and there's always been something where that hasn't worked. Questions up to here before I give you a slightly more depressing way of looking at this? Things tend to go to disorder, which also is worded as entropy increases. So think about yourself. All the atoms in your body are not just randomly put there. Every organ is in a specific place. Now, occasionally some people are born with things in a slightly different spot, but For the most part, most humans have a brain in their head. They have a heart somewhere around here, stomach somewhere around here, intestines, legs, arms, for the most, usually. And it takes energy in order to maintain that. Imagine if you have not eaten since you were a child. I do not think you would be here. It takes energy to maintain this. If I stopped eating, in other words, stopped supplying energy to myself, if I stopped eating, then eventually I would die and I would decay, and the atoms would then just sort of bleed into the ground, or however my body is disposed of. So in order to maintain your current form, you must keep supplying it energy. Let's think about it from a particle point of view. I have a slow particle here. Let's just start it out at rest. So I have this tiny little particle at rest. And I got another particle zipping along. Call this A and B. So B is at rest. What's going to happen when the A hits B? Let's make it a one-dimensional collision, just for fun.
It's gonna move it.
All right, so B is going to suddenly start moving faster. What about A?
A will slow down.
Yes. So B will speed up and A will slow down. Now, whether A bounces back or goes in the same direction depends upon the relative masses. Well, just for the sake of this, we'll just have A go in the same direction. So what happened was that they started out with very different amounts of energy, and then after the collision, their energies are much closer to each other than they were, because B speeds up and A slows down. Their energies start out very different, and then they end up roughly, or closer to the same. Given enough time, all particles will be going the same speed, or have the same amount of energy. At that point, when every particle is going has the exact same amount of energy, the collision can no longer transfer energy from one object to another. And when you can no longer transfer energy from one thing to another, then this is known as heat death. When everything is basically the same. And there's a fascinating video, I think, put out by someone called Melody Sheep, or a group called Melody Sheep, I'm not quite sure, where they look at, based upon what our current theories are in science or in physics, it projects out the next however many trillion years of the universe. And it ultimately ends with basically the universe is just a sea of particles. It's during this one, the one I'm going, all right, so what's the point of all this? If all in the end, if we're all just sort of a sea of particles. Because eventually the Earth is the sun will burn out. The particles of the Earth, the atoms in the Earth will start to drift apart. And the answer to the philosophical question is, ask Dr. Cannon, he'll know. And then, less depressing, the third law of thermodynamics. We will never reach absolute zero. I guess no system can ever reach, or a system will never reach. We will never be able to get anything down to zero, absolute zero. Let's see, how close have we gotten though? I've got that in here somewhere. Let's see, that was heat transfer. Not there. Oh, there we go. All right, so absolute zero, the closest that we have gotten so far is, all right, so absolute zero is negative 273.15 degrees Celsius, or negative 459.67 degrees Fahrenheit, or just simply 0 Kelvin or 0 Rankine. In 2000, we got it down to 280 picokelvin. Nope, sorry. That was 1993 record. That got beaten in 2000. 100 picokelvin. That is 0.0000000001 Kelvin. That is the coldest we've ever gotten anything. That was a piece of rhodium metal. The coldest gas in 2003 was 10 times hotter than that. So 1 nanokelvin, and that was sodium. And then the coldest molecule, so this was the gas, and then molecule, the coldest was 0.0025 Kelvin. And I didn't actually write down what the molecule was.
What would happen if you touch something that cold?
If you touch something that cold, it would basically kill the skin. And it was just sort of thinking, if you've ever touched something cold to your lips and your lips sort of stuck to it, then imagine that, of course, something that small. I would assume it would just basically kill everything that was near if you had something that cold. I probably should look up what's the coldest thing anyone's ever touched and find out what happened to them. We're probably dealing with such small quantities here that that's why I'm suddenly wondering, I'm not quite sure. Anyway, other questions? All right, now I want to just check to see if there's anything that I wanted to cover from these chapters that I have not. about that. Change of phase, we definitely did. Thermodynamics, we hit the major parts on that one. Okay. So in terms of assessments for these 4 chapters, we've got Wednesday and Monday are the last 2 classes before Thanksgiving. We have lab on Friday. So I should take some time to talk about the last test. Let's hit a couple things first. All right, so the assessment on these 4 chapters, what I'm inclined to do is not do a quiz on them, but you're still responsible for them, so please do the homework problems that are posted. Make sure you understand them. Unless there's a strong objection, that's the way I want to roll. These 4 chapters are not a major part of the last test, but I do feel free to ask 1 or 2 questions on it. So just be the major highlights. All right, the last test, because after Monday of next week, we will not see each other again, potentially. And actually, if I do see you, I probably won't recognize you without a mask on. And you sitting exactly where you're sitting right now. So, the semester ends December 9th. The way I work the last test, I guess, starting this past spring, you are not allowed to use a teacher or a tutor or anyone who teaches physics as part of the test. I'm not forbidding you from working with other people, other classmates on the test. However, I'm strongly discouraging it. The way I discourage people working together is that the more people who get a question right, the less the question is worth. So if you have a strong student and a weak student working together, most likely the weak student will get some problems that the weak student would not have gotten otherwise. But that will devalue it, and so the stronger student will actually end up being hurt as far as the grade goes. So I guess if you are a stronger student, it is, I guess, your conscience about how you want to deal with that. When you take it, I will probably open it up. Right now, my thinking is on, I think, December 7th. So Monday, December 7th, I will open it up in Blackboard. It'd probably be under assignments, and then there'll probably be a test. When you click on assignments, that'll be called test 3 or test 4 or test something. And I'll have an arrow pointing towards it, at least I've done that in the past, saying this is the one you want. Once you begin it, you have 2 hours to finish it. Now you can begin it any time from, right now my thinking is Monday the 7th in the morning until Wednesday evening. And at some point I will tell you the exact times. But again, once you begin it, you have 2 hours. I will know, I know how to look to see what time you open it up. And at that point, I will know when you have finished it because you'll have emailed me your answers. What I will probably do is I will post a PDF of the test. You can print it out, write your answers on it, and scan it and send it back, or take pictures and send it back, or some people will not print it out and they'll just write their answers on separate paper with solutions. I mean, show your work. But you're going to email me your, I guess, final version. If you do not finish within the 2 hours, and that's usually not a problem for 110, but occasionally it happens. If you are not finished at the 2 hour mark, send me what you have at that point. Anything that you send me after that, I'm going to count as test corrections. So you won't get full credit for it, but you'll get something for it, potentially. And that's where things are at the moment. Any questions about that?
Do you know like approximately how many questions will be on it?
I look at the old tests. Yeah, because I forget what I've done in the past. I assume it's similar in length to the first test.
And this is cumulative.
It is chapter 15 onwards.
15, okay.
Now, there's a good chance that we will not finish the vibrating motion, harmonic motion, basically the next 3 chapters before we break. But there are videos out there. You would go under course documents, chapter, and then whatever chapter we're on. And watch some absolutely spectacular videos with top-notch special effects. Or me with a piece of paper holding it in front of the camera. My videos have gotten more sophisticated than when I made most of those, but not by much.
Isn't Thanksgiving in 2 weeks?
It is, or a week and a half.
It's next week.
Yeah, 26. So we've got the rest of today, so we've got about another 15 minutes today. We've got Wednesday of this week. Friday we'll do lab, most likely the last lab. Monday class, and then that's it. Because Wednesday is faculty work day, the 25th. The day before Thanksgiving is faculty work day. Oh, class. How are we dealing with class during? I mentioned that there are videos. So the way that I picture it, I'm not planning to, have a Zoom meeting where everybody joins in and I sort of talk like we're in the classroom. The way I picture it is that during time that we have class, all of you presumably are free during this time. So I am going to be on Blackboard Collaborate. So I will be available, dedicated to this class during this class time through Collaborate. And I might need to create the button, I can't remember. In the spring, they were all created for us. In the summer, I had to create my own